back, people. Welcome back. Now we looked at a few gates before. If you didn't see our previous sessions, welcome, and please join the party. Subscribe so that in future you don't miss anything. If you find us interesting, we'll try to make it worth your while. Now we want to look at more gates. We've looked at the buffer, we looked at the NOT gate. Now what we're going to do is we are going to now say we are dealing with programming, by the way, and we're using the WPL soft for the Delta Corporation. So we are looking at how we use that to program. So I will look for something new. I want a new project. You know by now how to do this. Go to our previous sessions if you don't know, and then you say, I think I've got some clutter from previous work here. Let me just remove it. Okay, and then let's name our program. We're doing logic gates, and we are particularly interested in the Delta PLC, and then we want to do OR gate. Okay, now we have to name this according to the one that we have. Our model is the SS2. So there it is behind us there. This is the SS2, the TVP PS02. Now, okay, then there is our programming platform. All we do is make it large enough and we are happy now. So remember, we started off with the buffer. We said our buffer is simply, let me use the click. There is our X0. I'll choose 0. So if we have only one input driving an output, we saw how if the input is low, let's take out the output F7, and we want the Y, we're happy. So if there's one input, if it's low, the output will be low. If it's high, the output will be high. We say that's a buffer. We came and changed this and said, how about if this is, how about if this is a LDI, which means a closed. If this is a closed gate, if we leave it be, we saw how that was high, but if we activate it, we saw how that went low. So low on the input meant high on the output, and high on the input meant low on the output. We say that was a what? That was a NOT gate, otherwise called an inverter. Now we're going to say, okay, let's go back to our buffer. We have, with the buffer, we have the one way. We have the one way, we remove that I, it's only LD. We have the one way. How about if we say, what about we have another switch that can also turn on that same load? We say, okay, either that switch, or let's call it X1 load LD, and that will be X1. So either X0, we want either X0 or X1. So if the two are going to drive the same output, it obviously has to be what? A closed, a parallel arrangement like that. So now you can see you can close that line via X0, but you can also close that path via X1. So this is a two input situation. I have the X0 or the X1. So this is the OR gate. Now let's come and say, let's simulate this. I don't know what we're debugging there. This is too straightforward. It's just good practice. And then, all right, get out of debug, and we put online. You can see now it's on stop mode. Put it on start mode, on run mode. And then now you see nothing happens until we activate either set on X0 and you've got power, or if it's, because we don't want you to think it's because of the X0, let's remove this X0, we set off, you see it goes off, but now we set on the what? The X1, and again we have power. So either the setting on we either set on X0 or set on X1. Either X0 or X1 gives us power through the what? Through the power at the output. Now, what about if both of them are set on? Obviously, you've got one of them being redundant because the power is going what? It's going to go through anyway. All right. So this is unfortunately not an OR situation, because if I say U O, U, I mean one or the other. I don't mean both. So this is a both situation. Both of them are on, and we still have power. So if I said you or you, and both of you were to do it, that would be an AND. So this OR gate actually includes the AND state. All right. So what we mean here is that it's not exclusive to the OR condition. Hence the name inclusive OR. Maybe we should go back when we name it. We should rather name it the inclusive OR gate. This is what we call the inclusive OR gate, because yes, the one state x0 gives us an output. Let's set this off. We have the one state x0 giving us an output, and also the other state x1 on its own. If you get it on, we get an output. As you can see, our output is green there. So, but it also allows a situation that is not OR. If I say OR, we mean with the one or the other. It cannot be both. But in this case here, if you set both on, you still get an output, which is actually a what? An AND scenario. So this is why it is called an inclusive OR state, because it does include a state that is not OR. Let's. I would like to think that we've got these cases are discussed in our other digital systems class. So if you don't understand what you're talking about, can you please visit that class and maybe understand the logic case? We have a whole session on logic case, thoroughly explained. So please, when you come back here, probably things are going to be so much easier for you. So now, let us. What would we call this? What would be a more precise way of calling this, a more accurate way of calling this? This would be a two input. There's either the input x0 or x1. So this is a two input inclusive OR gate. That would be a complete way of calling it. It is the two input inclusive OR gate. Can we have more inputs? Of course we can have more inputs. And then, by the way, let's suppose we have the same situation, but the gates, the inputs were the same. Let's suppose it was x0. All right. Let's suppose this is what we had. Or let me say, okay. Let's suppose this is what we had. So both parts are actually x0, meaning they are driven by the same what? By the same component. All right. By the same condition. We don't have two conditions here. We've got one condition, which is x0. When x0 is low, it means now when I say this can be a typical exam question, right? When I say set this, or let's rather go on to simulate, debug, good practice, get out, and then go on to online, and then now we run. If you now set anyone, because it's one thing, if I set this on, obviously the other one goes on as well. So it's like you have a one input OR gate. It's like the input, your OR gate has got its inputs wired together. Your two input OR gate is like they are wired together. So this is how, if you wanted a buffer, this could be like a buffer, because now you have only one state. If it's on here, it's going to be on the other side. If it's off, it's going to be off on both cases. Let's set it off. Let's set the other one off, just to show you it works with either one. You set it off, both of them go off, and also that one goes off. So this is how a buffer can be made from what? From an OR gate. All right. If I don't care how many inputs there are, we could have a third input here. This was a T input. Let's add a third input. As long as it is the same one, let's insert here a row. There could be three or more. Let's say we have here another x0. Okay? And it is still an O. Okay? It is still an O. What am I doing? I'm looking for the line down. This is a three input gate what I'm trying to say is, this is a three input OR gate, but it has one common input. So it's like the inputs are wired together, right? Because whatever state the one is, the other ones will be too. Let's go to simulate. Okay. The sequence must now be automatic. Now let's go to simulate, and then now you can see when you say, do you wish to run? I do. And then now when I set anyone, you see that they all go on because they are named the same. It's the same thing. So this is like a one input. This is like a one gate. Okay, this is the equivalent of one gate. So this is the equivalent of a buffer. All right. I could have 5 inputs, for crying out loud. As long as they are all wired together, then they operate basically like a buffer. All right. So now, however, we had x1, x0, and x1. That was a 2 input gate. All right. Now let's rename these 3 inputs. We could have 3 inputs. This could be x1. Let me rather change that to x1, and the other one to x2. Okay, the other one to x2. Okay, x2. All right. And then what do you have? You have 3 different inputs, but they are wired in parallel. So it's an OR situation because our power can use the one way, the one route. Let me take a highlighter and take something bright. Now our power can go through the one way, or let's if x0 was closed, you can see that your line all the way to the output is closed. Or it could be the other one. You still have a closed path. All right, and obviously the other one as well, the last one, will still close the path. So either x0 or x1 or x2, when they are high, you have your what? You have your output going high. So these are 3 input gates. We could do it. You can see we can do it with 4, with 5, whatever. All right. So there's the concept of fan in and fan out. So sometimes you have to be careful because there are certain other things that we'll go into detail a little as we go. Now, what I want us to be aware of now is even combinations. If any 2 gates were set high, were set on, then the output will still go on. This is actually now the inclusive part. Okay, it includes a state. If I say, oh, it doesn't matter if there's 50 of you. If I say you or you or you or you all 50 times. If I say oh, as long as I use the word oh, the proper reaction should be a response from one of the 50, not all. So in this case here, the proper oh would be if I said any one of them and only one, then you would have what, and with an output in that situation, that would be a strictly or situation. But if a combination of them, if I say you or you or you, and out of 50 and 10 people stand up, it includes, if I accept that, it means I've accepted a non-or situation, because I've said or, but this and that and that and that, all these guys, 10 of them, they've stood up, or all 50 of you respond. That is what we call this is the inclusivity of the what? Of the or, of the inclusive or function. This is the inclusivity of the inclusive or function. All right. So what it means is, even if 2 were on, we still have power. Okay. Even if it was the one and the other. All right. Even if it was the one and the other, what I do. Even if, all right, it looks like I cannot. Even if it was a different, I'm trying to say Z. Oh, what is happening here? All right. I'm trying to undo my last action and it's undoing all the. All right, let me just erase. Okay, so even if I had said you, or you, and then x0, a lot happened when I said undo there. A lot happened that was not right. All right, let's go back and fix this first. Here we have a problem because we renamed this to x1. We rename this, oh, I didn't say okay. We rename this to x2. This is where I was trying to undo the pen and it was undoing my previous work. So now, so if I say you or you and x0 and x2 respond, it's not an or state, it's x0 and x2. If I say the same and then you see a response from, oh, the rubber, and then you see a response from x2 and x3, but there's x1 and x2. We started with 0. x1 and x2 responded. It's not a strictly or state because x1 and x2 have responded. So the inclusive OR gate, no matter how many inputs, does include non-OR situations where more than one gate actually what? More than one gate actually what? One input actually responds, when a strictly OR situation would have only allowed only one to respond. We are coming to that. It's called the exclusive OR gate. But for now, this is our 3-input exclusive OR. Let's remove the clutter so it's clear. Now, and there we are. We have ourselves a 3-input. Without the x2, with only x0 and x1, it was 2 input. Now with 3 inputs, it's a 3 input, and it is a 3. The proper way of calling it, of naming it, is a 3 input inclusive OR gate. 3 input inclusive OR gate. Alright, I hope you understood that gate. I hope you liked it. I think let's rather stop here. We'll hopefully you remember to like if you think it helped you, and then also please remember, if you haven't subscribed, please subscribe. Let's grow the family. And then last but not least, please comment there and tell us where you are. We want to know how far we are reaching. We want to know how far our effort is being disseminated. All right, so see you on the next run. I had fun. I hope you did too.